On December 30th, 2024, inside a steel chamber shaped like a giant metallic ring, China held a miniature star in place for nearly 18 minutes. Not seconds, not a brief flash. 17 full minutes of plasma burning at around 100 million degrees Celsius, hotter than the core of the sun, contained entirely by magnetic force. The machine is called EAST, China's experimental advanced superconducting tokamak. And with a sustained run of 1,066 seconds, it quietly pushed fusion research into territory that once seemed decades away. This was not a symbolic achievement. EAST had previously managed 403 seconds in 2023. Stretching that to over 1,000 seconds is not a small incremental step. It represents nearly a 2.6 times improvement in sustained confinement time, one of the hardest parameters in fusion research. 17 minutes may not sound dramatic. In fusion physics, it is a lifetime. Temperature alone does not make headlines in laboratories anymore. Multiple reactors around the world have reached temperatures above 100 million degrees Celsius. What makes the EAST milestone significant is duration under stable conditions. Fusion requires three things at the same time: extreme temperature, sufficient plasma density, and enough confinement time. This relationship is described by what physicists call the Lawson criterion. For decades, researchers have been pushing these variables separately. Sustaining them together is where difficulty multiplies. Plasma behaves like a storm made of charged particles. It writhes, twists, and destabilizes under tiny fluctuations. If it touches the reactor wall, it cools instantly and collapses. The breakthrough was not about heat, it was about control. EAST is a tokamak, a donut-shaped magnetic confinement device. Inside that torus, hydrogen isotopes are heated until electrons separate from nuclei, forming plasma. Powerful magnetic fields prevent this plasma from physically touching the chamber walls. Unlike conventional magnets, EAST uses superconducting magnets. These can carry large electric currents without resistance when cooled to extremely low temperatures, allowing stronger magnetic fields with lower energy loss. China's Institute of Plasma Physics has spent nearly 2 decades refining this system. EAST first achieved plasma in 2006. It was designed as a test platform for steady-state operation, rather than short experimental bursts. That design philosophy explains why long-duration confinement matters so much in its development path. This machine was built for endurance, not spectacle. To understand why this record matters, it helps to clarify what fusion actually is. Fusion is the process that powers stars. In the sun's core, hydrogen nuclei collide under immense pressure and temperature to form helium, releasing extraordinary energy. On Earth, scientists attempt to recreate this by fusing isotopes of hydrogen, typically deuterium and tritium. The energy density is staggering. Theoretically, 1 kilogram of fusion fuel could produce energy equivalent to roughly 10 million kilograms of coal. That comparison illustrates why fusion is often described as limitless. The fuel sources, especially deuterium extracted from seawater, are abundant. But abundance does not equal accessibility. To initiate fusion on Earth, hydrogen must be heated to over 100 million degrees Celsius. That is roughly 7 times hotter than the sun's core. At such temperatures, no physical container can survive direct contact. Only magnetic confinement can hold the plasma in place. Holding a miniature star in place is a physics problem unlike any other. Plasma instability remains the central obstacle. Small fluctuations can grow into disruptions. Magnetic reconnection events can cause sudden energy losses. Turbulence reduces confinement efficiency. Each second of stable operation requires constant monitoring and adjustment. EAST's improvement to 1,066 seconds reflects progress in multiple areas at once. Heating systems were optimized. Neutral beam injection and radio frequency heating maintained consistent plasma energy. Magnetic field shaping was refined to reduce edge instabilities. Diverter components made from tungsten helped manage intense heat flux, where plasma exhaust interacts with material surfaces. These are not cosmetic upgrades. Each component addresses a known failure mode in tokamak systems. Fusion advances do not come from one big invention. They come from solving thousands of small engineering limits. Artificial intelligence is increasingly integrated into plasma control systems. Machine learning models analyze real-time diagnostic data to predict disruptions before they cascade. East has incorporated AI-assisted control loops that respond faster than manual intervention could manage. Even so, it is important to separate record duration from commercial viability. East did not produce net electricity for the grid. It still consumes more power than it generates during operation. That remains true for every magnetic confinement fusion device worldwide. What the 1,066-second record demonstrates is stability under conditions closer to what continuous reactors would require. Fusion power plants must operate steadily for hours, not seconds. Extending confinement time is one of the most critical milestones along that path. The timeline did not collapse overnight, but it shifted. China's broader fusion roadmap includes a next-generation device known as BEST, the Burning Plasma Experimental Superconducting Tokamak. The objective of BEST is to achieve burning plasma conditions, where the fusion reaction becomes partially self-sustaining through alpha particle heating. That would represent another fundamental threshold in reactor physics. Meanwhile, East contributes data and technology to the international ITER project in France. ITER involves 35 countries and aims to demonstrate 500 megawatts of fusion power from 50 megawatts of input heating power. The lessons from long-pulse operations in East directly inform ITER's design refinements. Fusion research is not an isolated national contest. It is a distributed scientific effort. However, rapid iteration cycles matter. The speed at which improvements can be tested, validated, and expanded influences global progress. Fusion is a global race measured in physics, not headlines. The phrase "artificial sun" simplifies the story for public imagination. What actually happened in Hefei was more precise and arguably more impressive. Engineers maintained a superheated plasma loop in a magnetic cage for nearly 18 minutes without catastrophic instability. For decades, fusion critics have described it as permanently 30 years away. Records like 1,066 seconds do not invalidate that skepticism, but they reduce uncertainty. They show that some of the longest-standing technical barriers are gradually being pushed back. Temperature records were once the benchmark. Now duration is becoming the decisive metric. The longer plasma can be stabilized, the closer reactors move towards steady energy production cycles. The achievement does not mean limitless energy is available tomorrow. It means that one of the hardest scientific problems of the modern era continues to yield measurable progress. And in fusion physics, measurable progress is everything. Fusion progress does not happen in isolation. China's East record sits inside a much larger global effort that spans continents, political systems, and research philosophies. While East focuses on magnetic confinement and long-duration plasma stability, other countries are pursuing parallel approaches to the same goal. In France, the International Thermonuclear Experimental Reactor, known as ITER, represents the largest fusion collaboration in history. Backed by 35 countries, ITER is designed to generate 500 megawatts of fusion power from 50 megawatts of heating input, achieving what physicists call a Q value of 10. Construction is ongoing, and first plasma is expected later this decade. East's long-pulse data directly informs ITER's steady-state ambitions. Fusion is not one machine. It is a network of experiments feeding into a shared destination. In the United States, the National Ignition Facility achieved a different kind of milestone in 2022. Using lasers instead of magnetic fields, scientists briefly produced more fusion energy from a fuel pellet than the laser energy delivered to it. This inertial confinement method differs from tokamaks, but it proved that ignition conditions are physically possible. That success did not create a power plant, but it demonstrated that fusion can cross theoretical energy thresholds under controlled laboratory conditions. South Korea's KS-TAR reactor has also extended plasma duration at temperatures around 100 million degrees Celsius, while Japan's JT60SA is now one of the largest operational superconducting tokamaks in the world. The global landscape shows steady incremental gains across multiple platforms. Every region is solving a different piece of the same equation. Despite the momentum, major technical obstacles remain. Fusion reactions release high-energy neutrons that bombard reactor walls. These neutrons degrade materials over time, causing embrittlement and structural fatigue. Developing materials capable of surviving years of neutron exposure is a separate engineering frontier. Tungsten and advanced alloys help, but long-term durability at power plant scale is still under investigation. Another unresolved issue is tritium supply. Tritium does not occur naturally in large quantities. Future fusion reactors must breed their own tritium fuel by interacting neutrons with lithium blankets inside the reactor. Designing efficient and safe breeding systems is essential for continuous operation. The fuel cycle is as complex as the reaction itself. There is also the matter of energy economics. Even if fusion achieves net positive energy output, the cost of building and maintaining reactors must compete with renewables, fission plants, and emerging storage technologies. Fusion power plants will require enormous capital investment. Superconducting magnets, cryogenic systems, vacuum chambers, and radiation shielding are expensive to construct and operate. Scaling down costs while scaling up reliability is not a physics problem alone. It is a systems engineering and industrial challenge. Then there is continuous operation. Power grids require 24-hour reliability. A fusion reactor must operate steadily, not just in carefully managed experimental runs. Managing plasma instabilities, maintaining magnetic confinement, handling thermal loads, and cycling maintenance schedules must all align for commercial deployment. From laboratory triumph to power grid integration, the leap is enormous. Yet the potential rewards explain why governments continue investing billions. Fusion produces no carbon dioxide during operation. It does not rely on long-lived radioactive waste in the way conventional fission does. Fuel sources like deuterium are abundant in seawater. A successful commercial reactor could provide baseload power without the intermittency issues associated with wind or solar. Industries such as steel manufacturing, cement production, and hydrogen generation could decarbonize more rapidly if stable, high-output fusion power becomes available. Remote regions could access reliable electricity without relying on fossil fuel imports. The geopolitical balance of energy production could shift significantly if fusion becomes commercially viable. Energy abundance has always reshaped global power structures. Coal-powered industrial revolutions, oil defined 20th century geopolitics. Fusion, if realized, would represent another structural transition. The promise is not just cleaner energy, it is a different energy economy. However, experts remain cautious. Most projections estimate commercial fusion electricity arriving between the late 2030s and the 2050s. That timeline depends on ITER's progress, private sector innovation, and continued public funding. Breakthroughs accelerate optimism, but engineering realities impose discipline. China's East record does not mean fusion is solved. It means long-duration plasma confinement, one of the most stubborn barriers, is improving faster than many predicted a decade ago. It also demonstrates the value of iterative experimentation. East has broken its own records repeatedly over the past several years, showing a pattern of cumulative advancement rather than isolated spikes. If you want to stay ahead of the biggest scientific breakthroughs shaping our future, make sure you subscribe now